What is the main motivation behind the proposed method in the paper?
The main motivation behind the proposed method in the paper is to address the need for reference resolution in conversational agents, specifically focusing on resolving references to on-screen entities in addition to conversational and background entities. The paper highlights the importance of understanding context, including references like they or that, to enable natural communication with voice assistants. The proposed method aims to enhance the user experience by allowing queries about on-screen elements, thus enabling a true hands-free interaction. The paper emphasizes the limitations of end-to-end approaches in certain real-world scenarios, such as on-device frameworks with limited computing power or integration with APIs, which necessitate a more traditional pipeline approach. By advocating for the use of smaller language models fine-tuned for reference resolution, the paper aims to improve interpretability and modularity in handling different types of entities. Additionally, the proposed method seeks to overcome challenges in encoding on-screen entities for reference resolution by reconstructing the screen using parsed entities and their locations to generate a textual representation that aids the language model in resolving references effectively.
Why is it mentioned in the paper that there are cases where an end-to-end approach falls short and a traditional pipeline is valuable?
In the paper, it is mentioned that there are cases where an end-to-end approach falls short and a traditional pipeline is valuable because when a framework runs completely on device, such as on a smartphone with limited computing power, using a single, large, end-to-end model is infeasible due to the low-power nature of the system and latency constraints. Additionally, in scenarios where the model needs to integrate with APIs, consume information from upstream components, or provide information to be consumed downstream, an end-to-end approach would require a complete overhaul of existing pipelines, which might be cumbersome or completely infeasible. Therefore, in cases where efficiency, privacy, limited computing power, integration with existing systems, and the need for modular and transparent improvements are crucial, a traditional pipeline approach is considered valuable over an end-to-end approach.
How does the proposed method handle reference resolution for on-screen entities?
The proposed method for handling reference resolution for on-screen entities involves reconstructing the screen using parsed entities and their locations to generate a purely textual representation of the screen content. This textual representation includes tagging the parts of the screen that are entities, providing context around where entities appear, and the text surrounding them. By tagging entities on the screen, the large language model, LLM, is given information about the entity's locations and the text associated with them, enabling it to successfully perform reference resolution on both conversational and on-screen entities. This approach allows the LLM to see entities on the screen and understand their properties, facilitating the resolution of references to entities on the screen based on the textual representation generated from the parsed entities and their locations.
What are the 3 different types of relevant entities mentioned in the task formulation?
The 3 different types of relevant entities mentioned in the task formulation are on-screen entities, conversational entities, and background entities. On-screen entities are entities that are currently displayed on a user's screen. Conversational entities are entities relevant to the conversation, which can come from a previous turn for the user or from the virtual assistant. Background entities are relevant entities that come from background processes that may not be directly visible on the screen or part of the user's interaction with the virtual agent. These 3 types of entities are crucial for the task of reference resolution in the context of user queries and interactions with a conversational assistant.
How is the task of reference resolution posed for the large language model, LLM, in the paper?
The task of reference resolution for the large language model, LLM, in the paper is posed as a multiple-choice task. The goal is to extract the entity or entities that are relevant to the current user query from 3 different types of entities: on-screen entities, conversational entities, and background entities. The LLM is expected to output a single option or multiple options from the entities shown on the user's screen, with the possibility of also outputting none of these as an answer. The model is allowed to output the relevant entities in any order, meaning that any permutation of the correct entities is accepted as a valid output during evaluation. The task involves providing the LLM with relevant entities and a user query, and the model is tasked with identifying the entities that are pertinent to the user query, thus enabling effective reference resolution in a conversational assistant setting.
What are the two baseline approaches compared to the proposed model ReALM?
The two baseline approaches compared to the proposed model ReALM are the system proposed in Mars, which is a non-LLM based approach specifically designed for reference resolution, and ChatGPT, specifically the GPT-3.5 and GPT-4 variants of ChatGPT with in-context learning. The Mars system extends the approach focusing on on-screen entities to include conversational and background entities as well. On the other hand, ChatGPT, including GPT-3.5 and GPT-4, aims to predict a list of entities from a set available, with GPT-4 having the ability to contextualize on images for on-screen reference resolution. The proposed model ReALM, on the other hand, utilizes a fine-tuned LLM, Flan T5 model, with a specific pipeline for reference resolution, outperforming both Mars and ChatGPT in various datasets, showcasing its effectiveness in handling reference resolution tasks.
What is the key difference between the baseline Mars approach and the proposed ReALM approach?
The key difference between the baseline Mars approach and the proposed ReALM approach lies in the use of large language models, LLMs. While Mars is a non-LLM based approach specifically designed for reference resolution, ReALM utilizes LLMs, specifically a Flan T5 model that is fine-tuned for the task of reference resolution. ReALM advocates for the use of smaller language models, fine-tuned explicitly for reference resolution, as opposed to Mars, which does not leverage the power of LLMs. This difference allows ReALM to outperform Mars in all types of datasets, showcasing the effectiveness of using LLMs for reference resolution tasks. Additionally, ReALM's approach involves providing parsed input to the model and fine-tuning it, while Mars does not involve LLM fine-tuning. Overall, the integration of LLMs and fine-tuning for reference resolution is the key distinguishing factor between the Mars baseline and the ReALM proposed approach.
How does the proposed model ReALM perform compared to GPT 3.5 and GPT 4 in the results presented in the paper?
The proposed model ReALM outperforms GPT 3.5 and performs in the same ballpark as GPT 4 in the results presented in the paper. ReALM is able to outperform GPT 3.5 despite GPT 3.5 having a significantly larger number of parameters by several orders of magnitude. Additionally, ReALM performs almost as well as GPT-4 on on-screen datasets, even though GPT-4 is provided with screenshots for reference resolution. The results show that ReALM's textual encoding approach allows it to achieve competitive performance with GPT-4, which is a much heavier and slower model. The paper highlights that ReALM's performance gains are especially notable in on-screen datasets, indicating the complexity of the task. Furthermore, the analysis section demonstrates that ReALM and GPT-4 have similar performance on an unseen domain, showcasing ReALM's ability to handle new use cases effectively.
What is the significance of shuffling entities before feeding them to the model in the proposed approach?
Shuffling entities before feeding them to the model in the proposed approach is significant because it prevents the model from overfitting to specific entity positions. By shuffling the entities, the model is forced to learn the relationships and context between entities in a more generalized manner, rather than memorizing the order in which they appear in the input data. This helps the model to better understand and resolve references, regardless of the position of the entities within the input, leading to improved performance and generalization on the reference resolution task. Additionally, shuffling the entities ensures that the model learns to consider all entities equally, without bias towards any specific entity position, enhancing the overall robustness and effectiveness of the reference resolution process.
Can you explain the findings related to the performance of different model sizes on the on-screen datasets, as mentioned in the results section?
The findings related to the performance of different model sizes on the on-screen datasets, as mentioned in the results section, indicate that while performance improves in all datasets with an increase in model size, the difference is most pronounced for the on-screen datasets. This suggests that the task of on-screen reference resolution is more complex in nature. Specifically, the results show that increasing the model size leads to improved performance across all datasets, with the largest impact seen in the on-screen datasets. This highlights the importance of model size in tackling the complexity of on-screen reference resolution tasks. The findings suggest that larger models are better equipped to handle the intricacies and nuances of on-screen references, resulting in enhanced performance on these specific datasets. In essence, the study demonstrates that for tasks involving on-screen context, having a larger model size can significantly boost the model's ability to accurately resolve references and extract relevant entities from the screen data.